Recapitulate this advantages of linear systems state space representation one more time. So, this is first we go for state space representation because it gives us a systematic analysis and synthesis tool for higher order systems, and we have seen couple of examples in the last class to get getting ourselves comfortable with this idea actually. And we do not want to do any truncation of the system dynamics here, that the state space representation gives us that framework. Second thing, it is convenient tool for MIMO systems. Okay. Then it is a uniform platform for representing many systems like time invariant, time varying, linear system, nonlinear system, whatever it is. Then it gives us some sort of it can describe system dynamics for almost all systems, mechanical, electrical, biological, economic, social, all sort of systems. We have primarily confined ourselves for mechanical systems, but that is where aerospace engineering falls actually. Okay. So, then also remember that transfer function representations are only good for linear time invariant system. So, with that in mind, we will proceed further to the next class actually. Okay. The topic here what we discuss is something like this. Now that we know that state space representation is possible for linear systems and transfer function representations are there in linear systems already, is it possible to have conversion between the two? That means, if I know state space representation, can I transfer it to transfer function and vice versa? There are certain good things out of that actually. If I represent the system dynamics in transfer function domain, there are certain nice analysis I can do, certain inferences I can do in a big way, good way rather, and so similarly in the state space representation as well actually. Okay. So, the question turns out, for example, if you really want examples, for example, transfer function representation gives us something like a phase margin, gain margin concept, that is a robustness concept. We want to see it from that point of view, let us say, and state space representation gives us the idea of controllability, observability, that is another big thing actually. So, we want to have some sort of a conversion if it is available or not actually. So, the question is like this, we know the state space representation form is something like this, and the transfer function representation form for single input single output is something like this, right, kgs divided by 1 plus kgs, k of g of s into h of s. Now, as I told the question is conversion between the two forms possible, and it turns out that the answer is yes, it is possible. Okay. So, let us see how it is possible. Now, first we see that how to derive transfer function model from linear state space models actually. That means, this state space model is known to us, somebody has given us already, and what we are interested is in deriving some sort of a transfer function representation. Okay. How do we do that? Now, let us start with this. Okay. These two equations, because it is known to us, we will take Laplace transform, okay, and assume standard 0 initial conditions everywhere. The linear systems response is not they do not depend on initial conditions. Linear, the properties of the linear system are independent of initial conditions, that is why 0 initial conditions are there. So, we take Laplace transform both sides, both of the equations, and we arrive at that. Remember, there is x dot will give us s into x of s in a vectorial sense, component by component if I take, I will be able to do this actually, and A is a constant matrix, B is a constant matrix, that will fall out here. Similar things C and D will also fall out outside actually. So, this is where we will get this expression is coming from the first equation, second expression is coming from the second equation actually. Now, we will do a little more further analysis and see that x of s and x of s are together here. So, let us try to solve for x of s, because that is what we need here. What ultimately we want to need is a relationship between input and output. So, output is here and input is here. Okay. So, we want a relationship between y and x actually, and then this is coming somewhere in between x of s, we want to eliminate that actually. Okay. How do we do that? We will be able to do that taking help of the first equation here. So, let us do that. So, if I take the first equation, okay, and try to see this is if I want to bring this one to the left hand side and try x of s common, then I have to do this algebra s into I minus a, remember that, because this has to be a matrix actually what you see here, and in a vector sense if I write it s into x in a component by component multiplication, in a vector matrix sense I have to do s I minus a here. Okay. So, this is s I minus a into x of s is equal to b times u of s actually. Okay. So, what you see here, this same equation s I minus a into x of s is equal to B times U of S, that is what is written here. So, if I pre-multiply both sides by Si minus A inverse, then the first one is identity, that is gone, but this will come to the right hand side. So, it is Si minus A inverse into B times U, that is what will happen here. So, now I got a solution for x of s. So, I will go back and try to plug in here whatever s of x of s I got, and then I am done, because this is what will give me y of s is C of s into Si minus A inverse into B plus D, okay, that is because that D comes from this D actually. Okay. So, that is what will happen, C into Si minus A inverse plus into B plus D into U of s actually. So, this expression what you see here is nothing but you can represent this as some sort of a T of s. Okay, that is what we have seen before, but T of s is not possible to write y s by U s in general, because y s by U s is by writing that you are assuming single input single output again. This is multiple input and multiple output, that means this is a vector and U of s is a vector, some vector by some vector is not defined actually. Okay. So, we will most likely in in all possible cases we will just stop here and tell this a transfer function matrix T of s, okay, whatever matrix is coming up here, in the sense that y of s is equal to T of s into U of s. Okay. Some books will write y of s by U of s, but that is just a notation, that is not an algebra. Okay. Y of s by U of s is not defined in terms of algebra. Okay. In algebra they mean this one only, y of s is equal to T of s into U of s, and T of s expression is given by this C into Si minus A inverse into B plus D. Okay. And remember, this is actually a unique way of doing this. The moment you know A, B, C, D, this is the T of s. There is no dithering, there is no second expression available actually. So, that means converting from state space to transfer function representation is always unique, and this relationship is given by that actually. Okay. Now, example sense, if we talk about a simple example that we discussed last class, probably this is 0, 1 and minus 2, minus 3. And then 0, 1 actually. This is, so we knew this A, B, C, D matrices. So, can we talk about a transfer function? Remember, this is a scalar input, this is a scalar output. So, it is actually a SISO, single input single output system. So, I can still write y s by U s. So, I will not carry out all the steps again, I will simply apply this formula. Remember, D is 0. So, I will simply apply this formula what I have, C into Si minus A inverse times B, D is 0 anyway. So, if I do this algebra, it will turn out to be like this. How is that? Let us see the algebra. C into Si minus A inverse plus into B plus D. So, C is this, Si turns out to be a 2 by 2 matrix. So, this is S and S here, 0 0 here, this is Si minus A is what you have here. So, I will just pick up A from there. Okay. So, this is Si minus A, the whole inverse I have to take, okay, into multiply by this B matrix what I have, then plus 0 actually. So, if you simplify this actually this two subtractions first, it will turn out to be S here and 0 minus 1. So, it is minus 1 here, 0 minus of minus 2, that means plus 2 here, and then S minus of minus 3, that means S plus 3 here. Okay. So, you have C, you have Si minus A, and I have to still take inverse of that, then I have to multiply with B, then D is 0 anyway actually. Okay. Now, C is here, then this matrix inversion for a 2 by 2 thing it is very easy. You have to do 1 by determinant of that, and determinant is this one S into S plus 3 minus of minus 2, that means plus 2 here, this 1 by determinant of that. And as far as the adjoint matrix is concerned, for a 2 by 2 it happens that okay, you can extend these two elements and you can change the sign of these two elements. Okay. So, you can extend these two elements to S plus 3 will go here and S will come here. Okay. You can see that from the adjoint matrix formula, it is very clear actually why it happens. Okay. So, 1 by determinant into adjoint matrix, and the adjoint matrix for a 2 by 2 is diagonal elements will exchange place and off diagonal elements will change their sign actually. Okay. So, you take minus 2 and plus 1 here, and then you put it there, and then you are ready with some sort of a matrix here, not matrix inverse anymore. So, this is a scalar, so I will take it out, and this is a square plus 3s plus 2 which will come out here. Then this is C matrix. Okay. Then these two matrix if I multiply, 0 into S plus 3 is 0, plus 1, 1 into 1 is 1, that is why 1 is there, and minus 2 into 0 is 0 plus S into 1, that is S actually. Okay. Again if I multiply these two quantity, this is 1 plus 0. So, ultimately I am left out with 1 actually. Okay. So, this entire algebra T of S is nothing but that is what you get it here actually. Okay. So, that is conversion from transfer, I mean state space to transfer function actually. Okay. Now, can it be possible? Is it possible to do the reverse actually? Okay. That means, we want to derive the state space model from transfer function this time. Okay. And unfortunately, this happens to be non-unique. That means, this conversion process what you see here, okay, is certainly not unique. You can do it one way, I can do it other way actually. Okay. So, each of that getting in that ABCD matrix from a transfer function representation is something called realization actually. Okay. So, obviously, because this process is not unique, there are various realizations possible. Okay. But it turns out that all realizations are equivalent. Okay. That means, the properties do not change actually. Okay. The properties of stability especially or controllability, if you see, though they do not change. However, some representation may have some advantage over the other for a particular task. For example, if you go for control design, then probably most likely will opt for controllable canonical form. But if you talk about some sort of a observer design or filter design, probably the natural choice will be going for a second companion or observable canonical form. Okay. There are certain advantages, especially this numerical computation algebra and all sort of thing. There are advantages by doing one form of realization over the other actually. Okay. So, but nevertheless, also remember that all realizations are equivalent, that the properties normally do not change too much actually. Okay. Now, possible representation, we have already seen what is called as first companion form, which is also known as controllable canonical form. There is alternate first companion form possible, the second companion form possible, the Jordan canonical form possible. Some of these forms we will see, and this is not an exhaustive list by the way. There are various realizations people have done. An extensive course on a linear systems theory probably will tell you some of these more detail in a rigorous way. But here we are interested in getting the ideas in a proper way. Let us see one at a time. The first companion forms is something that we have already discussed in last class. Just to recapitulate, this is the form that this is the differential equation. Suppose you start with, okay, and we have not started with a transfer function. Remember that, but we will soon tie up with this actually. Okay, let us start with a differential equation. Then we have seen that okay, these are the ways to define the state variables. Okay, and this is the derivative, I mean x1 dot x2 dot all will fall in that way. Okay, and then taking the help of the last equation, it is possible for me to write it this way. So, we discussed that all the details in last class actually. Now, if you see this realization, okay, why you are studying this primarily is because suppose we given an nth order transfer function, okay, it is possible to write this system equation in this form actually. Okay. Once it is written in that form, differential equation form, then we will be able to proceed further this way. Okay. We will see that in an example also. Okay. Now, if you see this representation, what you see here, now really want to realize this system in a let us say hardware design and things like that, how do you go there, how the system signal flow takes place actually. Remember this, the definition sense, what I am telling is x1 dot is x2, x2 dot is x3, things like that actually. So, I will put an integrator first, let us say on the line, first row actually. Okay. And what is happening, x1 dot is x2, that means x2 integral is x1. Okay. And similarly, if you see xn dot is integral of that is xn. So, there is xn dot here, integral dot of xn, integral of that is xn minus 1, it will all the way continue up to x1. So, these n integrators I will put it first actually this way, and now I have xn dot to take care here. Okay. And this xn dot is nothing but this expression actually what I see here. Okay. So, this is something like minus a1 times xn minus a2 times xn minus 1 like that actually. So, if I see this diagram what I see here is this is x1 a1 times xn, a2 times xn minus 1 all taken together, all the way sum together with a negative sign here ultimately, okay, plus u, and u is coming directly here that way. Okay. So, xn dot is constructed through all these integrators with multiplication of a1, a2 and a3 all that sum together and then finally summed with a negative sign actually. Okay. So, that is the way to kind of realize this n integrators actually. Okay. Now, an example we will see. Okay, this let us start with this example actually. Remember this is a transfer function representation. Okay. Now, starting with this transfer function, what is the meaning of this transfer function? Cs by Rs is this transfer function, right. So, if I start with that, then this into Cs, okay, whatever this denominator into Cs is equal to numerator into Rs, right. Cs by Rs is this expression. So, Cs into denominator is equal to Rs into numerator, okay, that is what is happening here. Now, if you go back to your Laplace transform ideas, then x q means third order derivative, s square means second order derivative, like that actually. So, you will end up with some equation in the differential equation form, the third order differential equation, and again we will go back to this system variable representation and things like that. So, we will discuss, okay, x 1 is equal to c, I think there is a small print mistake here, okay, x 1 is c, x 2 is c dot and x 3 is c double dot. Okay. So, then x 1 dot is x 2 and x 2 dot is x 3 and x 3 dot is actually all these things that you see here, okay, and that is something like x 3 dot will give us this expression actually. Okay. So, y equal to c if I take, then that is x 1. So, I will be able to proceed further, okay, and then write it in the form of state space representation. That is all if I have a constant term in the numerator. Okay. Now, what happens if there is a polynomial in the numerator, that is also very much possible, right, in a transfer function need not be a constant term actually. Now, the same trick applies. What you do is this transfer function, what you see here, I can represent that as multiplication of two blocks actually. Okay. One will be the 1 by this term, then the next block will be multiplication term that way. And we are all talking about proper transfer functions, remember that. That means, the order of the numerator polynomial is less than equal to the order of the denominator polynomial, and strictly proper means it is strictly less than that actually. Okay. So, here is a strictly proper transfer function, we are decomposing that into two blocks, one in this block, one in the other block, and this particular block we have just studied actually, right, other than the 24 constant, okay, which really comes here. I will, if it is 1, this 1 will come here actually, okay. That part is already know, okay. And also remember, that is the way to realize also, there are 3 integrators here, okay, x 3 dot, x 2 dot, I mean x 3 dot integration will give us x 3, x 3 integration will give us x 2, x 2 integration gives us x 1, then multiplying with that appropriate constants what I have, and then sum it out together with a negative sign actually. Okay. So, that is what happens here. Now, coming back to this example, this is 1 here. So, we will have 1 there, that means this part of the equation that is already known to us. Okay. Now, what happens to the output actually? Output happens to be as this polynomial into x 1, right. Okay. So, this polynomial gives me something like x 1 double dot plus 7 x 1 dot plus 2 x 1, and x 1 double dot is nothing but x 3, x 1 dot is nothing but x 2, and x 1 is nothing but x 1. So, the output equation is something like this, x 3 plus 7 x 1 plus 2 x 1, x 3 plus 7 x 2 plus 2 x 1. Okay. So, the state equation remains same and the dynamic equations remain same, but the output equation takes this form actually. Earlier remember it was just 24 just x 1, sorry. Okay. Now, it is not only x 1, but it is like this actually. How to realize this? Again this bottom side of the story remains same, okay, because the state space realization remains same. Okay. And then you talk about the top side, you take this branches out here. Okay. Remember this is x 3 plus 7 x 2 plus 2 x 1. So, there is x 3 component, I will take it through 1, there is x 2 component, I will take it multiply through 7, there is x 1 component multiplied by 2, then sum them together I will get y. Okay. So, that is how I represent actually. Okay. So, systems having what about generalization, further generalization? We will talk about a single input, but multiple outputs. These are all single outputs, what we saw there is y, right, single outputs actually. How do we generalize for multiple outputs? Again remember that A and B matrices will remain same, but C and D matrices will get modified. Let us see an example for that. Let us talk about two equations, y 1 by u of s and y 2 by u of s, h 1 and h 2 given by this polynomial, and mostly the denominator polynomial will remain same. That is how the system transfer function representation will pop up actually. Once the denominator remains same, but the numerators are different actually. So, remember this is 2s plus 3, this is 3s plus 2 rather. Okay. So, what will happen? This h 1, okay, what I see here, okay, y 1 by s, okay, then this y 1 by s, okay, I will represent this polynomial what I see here, okay, as I will multiply and divide by z of s actually rather. Okay. And what this z of s? I take the z of a is nothing but 1 actually. Let me represent it that way. Okay. So, this is 2s plus 3. I am remember this, I am still analyzing only h1, h2 I am not considering here. Okay. So, I know h1, I will represent it that way. Again, this is a multiplication of two blocks, right, is not it? First block, and I can multiply both ways. I mean, this one I can always put it in the right hand side actually. Okay. So, then I will get again similar things what we discussed before. Okay. I will define, let us say x1 is z and x2 is z dot, and hence I will from this polynomial what I see here, okay, the denominator part, this right hand side of the story, okay, this part which corresponds to right hand side. From there I will talk about, I will be able to extract this equation x1 dot and x2 dot actually. Okay. Right, and then I mean this 3 what you see here, okay, will actually divide by for everywhere, right, by that 4 by 3, 5 by 3, that kind of expression will come. Okay, you can do the algebra little detail actually. So, the equation will turn out to be something like that, 4 by 3 plus 5 by 3 equal to 1 by 3 u. So, then you define x1 and x2 that way, and then this if you do that algebra, that is x1 dot is z dot is x2. Okay, again same thing will pop up here 0 1 and 0, okay, and x2 dot is nothing but z double dot, and z double dot is all these equation in the right hand side. So, if you put them together, it is 1 by 3 into u. So, that is 1 by 3 comes here, minus 4 by 3 into z dot, that is z dot is x2. So, that is where it is, minus 5 by 3 into z actually, that is why it comes here. So, this expression is given like this, x1 dot x2 dot together like that. Then output equation is given as 2 times z dot plus 3 times z, right, 2 of z dot 2 times z dot plus 3 times z actually. So, that is where you go back and see what is z and z dot, there are simply definitions actually, right, z is x1, z dot is x2. So, y1 is nothing but that. So, in a vector matrix representation, it turns out to be 3 2 which is my C matrix and plus 0 times u, that is my D matrix actually. Okay. So, this is my A, this is my B, this is my C, this is my D in this way of realization basically. Okay. Now, H2 will see what is H2 here, okay, and H2 is the second one, okay, and second one remember that is that comes from this actually, this expression. So, this 1 by term will remain same, 1 by 3s square plus 4s plus 5, that will remain same, that is what remains intact, and then instead of 2s plus 3 we will have 3s plus 2. So, obviously A and B matrices are same, we have discussed that before, whereas this y2, okay, if you discuss about that, this is 3 of z dot plus 2 of z is equal to, again going back to the definition and all, this is 3 of x2 plus 2 of x1 actually. Okay. So, this is 2 times 2 into 2 3 which will come here times x1 x2 plus 0 into u basically. Okay. So, the block diagram representation is again fairly straightforward, and also remember that no matter whether you have multiple input and multiple output, but same input with same polynomial here, then the state equation remains same. That means, the number of integrators that you need to represent the system dynamics or the number of state variables, that remains same actually. Okay. So, it is the system is still realizable with n integrators here actually. Okay. The realization requires n integrators only. Let us go to a very different form of representation. See, that is what we discussed about first companion form all the time actually. Okay. Now, there is a very different notation, okay, which comes from what is called as the Jordan canonical form, and this is its own beauty actually. Like if you go back to the matrix representation and things like that, we will discuss those matrix algebra in couple of classes later in fair details actually, okay, whatever is necessary for this particular course actually. So, it turns out that there is some matrix transformations there, okay, and then if you given a matrix whatever n by n matrix, can you reduce it to some form or some simple forms and all that actually, and those simple forms will lead us to something like one reduction, what is called a similarity transformation and all that. The similarity transformation will reduce a matrix A to matrix B to certain invertible transformations actually. Okay, we will see those little down the line actually. Now, what happens is in those simplified form, the meaning turns out to be little more appropriate actually. Okay. That means, if you really have some sort of a matrix form, okay, let me try to demonstrate that a little bit further probably. Now, let us say you have something like a matrix A. Okay. Now, the idea is can I get an equivalent representation in some form or other, tying up that with matrix B basically. And it turns out that I can do this thing by P inverse multiplying this and P here. Okay, where P is given by certain eigenvectors and all that. Let us say I compute eigenvectors for this V1, V2 like that. I put this in the form of matrix, I mean this Vn, okay, and whatever is that V1, V2, V3, these are nothing but the eigenvectors of this matrix actually. Now, this turns out to be something like a non-singular okay, matrix. Okay. And now, if I carry out this algebra what I have here, then this B matrix interestingly turns out to be a very nice form actually. And sometimes if these eigenvectors are linearly independent, okay, that is a primary requirement actually, then what happens is this B matrix that you see is nothing but a diagonal matrix, that is all. Okay. This is the simplest form that is possible. And knowing B and P, I can always recover A, because A is nothing but P times B into P inverse, right. If I do that same backward algebra basically, then this turns out to be from this expression and these two expressions are equivalent, okay, as long as the P matrix is non-singular actually. Okay. And this P matrix turns out to be non-singular if all these eigenvectors are linearly independent actually. So, that means what I am doing here, I am getting some sort of a diagonal matrix, and not only that, I will get diagonal elements say something like lambda 1, lambda 2 all the way up to lambda n, where these are nothing but eigenvalues of a matrix. Assuming that these guys are this lambda 1, lambda 2, all these are some sort of I mean different numbers actually, they are not same numbers, okay, then it will happen actually, everything will happen nicely. Now, if they are same, okay, the question turns out to be, I mean what if they are same actually. Okay. Now, if they are same, there are two cases which may arise actually. Okay. In some cases, you may still be able to get linearly independent eigenvectors. Okay. Then it is still possible to reduce this into a diagonal form actually. And then if it is not possible, then it turns out that it little more general sense. Let us say you have repeated eigenvalues, which for some of the repeated eigenvalues you really do not have linearly independent eigenvectors. Then what you will do is the corresponding element, let us say this V1, V2, V3 correspond to let us say same eigenvalue lambda 1, V1 and V2 are independent, but V3 is not independent let us say. Okay. Then in that particular case, this V3 is no more an eigenvector, but this will consider as something called generalized eigenvector. Generalized eigenvector. Okay. If it is generalized eigenvector, then it will turn out to this will no more be a very specific form, sort of what you look at it very nicely. Then it is actually what you are having here, lambda 1 is independent, but what you have is lambda 2 let us say. Okay, this is repeated actually. So, in this case what we will have is lambda 1, lambda 2 here, this is 0 here and things like that, but here you will have 1 actually, not 0. So, these are all like, but it is still much simpler than what you really like to have actually. These are nothing but Jordan blocks and all that actually. Okay. So, if you have a real 0 here, okay, instead of 1, then you have a diagonal matrix actually. Okay. But instead of that you will have 1 actually, but still it is a much simplified form because all other elements are 0 anyway. Okay. So, that is where things are easier to analyze. They have much more physical meaning as well. That means, these eigenvectors typically represent some sort of a principal axis in the system dynamics. Okay. For example, if you take some sort of something like a piece of paper and try to apply force to tear it off this direction as well as this direction. Okay. These are all forces applied, like let us say two people are pulling this actually in two different directions. Then the way assuming that homogeneity of the paper, I mean paper properties are homogeneous and all that, the tearing thing will not happen either of the direction. The tearing thing will happen in some other direction, right. Okay. This direction it may happen in these two directions actually, depending on resultant forces and things like that, where it will act, where the paper is weakest and things like that actually. Okay. These are nothing but principal directions actually, those are nothing but eigenvectors essentially. Okay. So, these the concepts what we will study in matrix theory a little bit later down the line will all tie up nicely with this system theory basically in a way. Okay. So, if you have a transfer function representation somewhere, it in some cases it will be very advantageous to us to represent that in terms of a Jordan canonical form. And this is, I mean, going back to this example, these are what you call a Jordan blocks actually. Okay. And this essentially this representation is nothing but Jordan Jordan transformation, what you are talking, A equal to P inverse B P sort of similarity transformation will lead it to some sort of a block matrix here, actually block diagonal matrix in a simplified way. Okay. So, that is where that name of Jordan canonical form comes and all that actually. So, you really want to analyze what is happening in this principal axis directions essentially. Okay. So, that is that is what you are interested in actually. Okay. Now, let us go back to that, okay, and see what is what is going on here actually. So, let us represent this, okay, in the form, let us assume that there are non-repeated roots. Okay. That means, the transfer function that you are talking about h of s has denominator and numerator, right. So, we are all concerned about the denominator first, that is what will give us roots actually, right, the eigenvalues, roots and things like that actually. And here we are assuming that there are the roots are non-repeated. That means, and the roots are nothing but lambda 1, lambda 2 and all that actually. And remember, this is specific reasons for considering them as this lambda 1, lambda 2 symbol. They are nothing but eigenvalues actually. Once you see that realization, it will turn out to be eigenvalues actually. Okay. So, anyway, so these are the roots of the polynomial, and what you are assuming here is lambda 1, lambda 2 up to lambda n are non-repeated, and hence the eigenvectors corresponding to those elements of lambda 1, lambda 2 after realization of this A matrix and all that are will turn out to be linearly independent. Okay. I mean, just to remember that actually. Now, what happens here is, okay, if it is linearly independent, I mean, if it is non-repeated, then this polynomial what I have numerator by denominator, I will always be able to factor it out this way, assuming that this is the most general way I can have actually, right. Assuming that these are non-repeated, that means the numerator by denominator what I am talking here. Okay. Let me probably go back to that little bit here to analyze a thing. Okay. Let me clear the board first and then we will talk about that. Okay. All right, let us talk about that. So, you have something like transfer function, which is nothing but numerator by denominator polynomial. What you are doing here is d of s equal to 0, that is what you are doing. Okay. And we are assuming that numerator polynomial is of nth order, n plus something into s minus n like that actually. Okay. Denominator polynomial is also of nth order basically. Okay. And remember, this may not be same coefficient by the way. So, okay, something like that. So, if there is a if it is there, then I can always divide this polynomial, and what I can write this t of s as something like b 0, which will come from this coefficient analysis and all that. I will make this plus or minus multiplication, division, all sort of thing. So, I will take out a b 0 component, and then I have some this polynomial what you see here in the denominator is nothing but s minus lambda 1 into s minus lambda 2, okay, like that it will carry up to s minus lambda n actually. Okay. And then after I take out b 0, the remaining polynomial is strictly proper. That means, it does not anymore contain the power of n actually, it contains the power of n minus 1 onwards actually. Okay. So, that is why I will be able to write it in the form of b 1 divided by s minus lambda 1 plus b 2 divided by s minus lambda 2 all the way actually, plus b n divided by s minus lambda n, and that is what I am doing there actually. Okay. So, let me go back to that and then see what is going on here actually. Okay. That is what is being done here actually. Okay. So, I am starting with this y of s divided by u of s, with assuming that I can be able to do that actually. Okay. And with the assumption that all poles of the transfer functions are distinct, that they are not same, and there are no repeated poles actually. Okay. Very specific case, we will try to generalize that also. Okay. Now, what is the, we all know that R 1, R 2, R 3 all the up to R n, these are all called residues of the reduced transfer function, right, H s minus B 0 if I take that H of s minus B 0 what I discussed there. These are all residues of that that transfer function that is left out actually. This is just by definition sort of thing. Okay. Now, if I have this is what I started with this form actually. Okay. Then what I can do, I can multiply this u of s to the right hand side and tell that is okay, y of s is nothing but B 0 times u of s, okay, plus R 1 divided by s minus lambda 1 whatever I have into u of s plus R 2 by s minus lambda 2 into u of s like that actually. Okay. Right. This expression what you see here simply comes from the first equation. Okay. And then what I see is my definition of state variables are different here actually. Okay. I am defining my x 1 of s to be this quantity what I have here, okay, defining x 2 of s to be that quantity what I have here, defining x n of s, remember these are all in Laplace variables yet actually, okay, is to be that quantity. So, this is my x 1 of s, this is my x 2 of s, this is my x n of s. Okay. Now, if I know this variable like that, I mean this equation like that, let me multiply now actually. If I multiply this now to the left hand side and interpret the differential equation, then this is s into x 1 of s, that means x 1 dot, okay, minus lambda 1 into x 1 of s, that is lambda 1 into x 1 is equal to R 1 into u. Okay. So, this is like that actually, this is x 1 dot minus lambda 1 into x 1 is equal to R 1 into u. So, similar thing I can do for all these things, and I will represent this differential, this all will pop up as 1 first order differential equations actually. Okay. This is x 1 dot minus lambda 1 x 1 is equal to R 1 u, next one will be x 2 dot minus lambda 2 x 2 equal to R 2 u, similar thing will go on to x n dot minus lambda n into x n is equal to R n u. Okay. I hope this is clear. Then what happens is, okay, I will take this quantity to the right hand side, that is all I will do, x 1 dot is equal to lambda 1 into x 1 plus R 1 u, like that I will write actually. Okay. So, if I write that, and ultimately what it happens, x 1 dot is nothing but lambda 1 times x 1 plus R 1 u. So, this is lambda 1 times x 1 plus R 1 u, because all the elements, all other things are 0 actually. Okay. Similarly, x 2 dot is lambda 2 in the diagonal into x 2 plus R 2 into u. Okay. Now, see all these things I will be able to write it that way. Okay. Right, x n dot is equal to lambda n into x n plus R n u. Okay. So, if you see each of the rows of the A matrix, only diagonal elements will be non-zero, all other terms will turn out to be 0. So, naturally what you get here, this A matrix is actually in a diagonal form already. Okay. But the B matrix is not 0 0 0 0 and last one element is 1, that is not there actually. All of the elements that you get is R 1, R 2, R 3 up to R n actually. So, that is your B matrix actually. Okay. Now, coming to the C, and still remember that if it is my output is given by this expression, right, y of s is all this actually, remember that. So, y of s is nothing but B 0 u s plus x 1 plus x 1 of s plus x 2 of s plus x n of s actually, all these things are available for me. So, as far as y 2 is concerned, it is all x 1, x 2 plus x 2 plus x 3 plus up to all the way up to x n plus B 0 times u s actually. Okay. So, that is what I will keep it in this way. So, y of t is nothing but x 1 of t plus x 2 of t, x 1 of t plus this one into this, that is x 2 of t plus x 3 of t, like that actually. So, this is why I will get my C matrix as 1 1 1 1 1 1 all the way, I mean that is a C vector, and then this is a B 0 component will also be there. Okay. So, that means this B 0 is coming directly from here. Okay. So, that is what will happen to be like that B 0 sitting here actually. So, this is your A matrix, this is your B matrix, B vector rather in this case, this is your C vector and this is your B 0. And if you started with if you start with something like a strictly proper polynomial, then this component will not be there, this B 0 will not be there. So, that B 0 will not come here either actually. Okay. So, and most of the systems are that way. So, what is the difference between this first canonical form to Jordan canonical form? You can see clearly that the matrix turns out to be diagonal, that is the big advantage. Okay. And these are nothing but, remember the diagonal matrices, the eigenvalues are diagonal elements directly, they are the diagonal elements. In general, if it is a triangular matrix, the eigenvalues are diagonal elements, that you can see it from the definition of eigenvalues actually. So, these elements, what you saw that is roots of this characteristic, I mean roots of the denominator polynomial equated to 0 is nothing but the eigenvalues of this system matrix actually. Okay. And we will see that later, that the stability behavior of this system dynamics largely depends on, I mean only depends on the eigenvalues actually. So, that is what happens actually later. Okay. So, this the way, suppose you started with this transfer function what you had and went ahead and did that first canonical form, then the A matrix turned out to be in a different way. I think we can see some of these examples also, like you can, if you go back there, the A matrix turns out to be that. So, certainly the eigenvalue information is not as clear as the other one. You really have to do the eigenvalue analysis in the characteristic polynomial and things like that to find out what are the eigenvalues in this form. But in that form it turns out to be very natural, it just available for you actually. Okay, that's already there for you. Okay. However, the B, C and D matrix, so we have to be slightly careful actually. So, earlier the B matrix turns out to be 0 0 0 0, the last element was some number, here it is all the elements will have some number actually. And why that happens? That primarily happens because of the change of the definition of x 1, x 2, x 3. It is no more your see first companion form, the state variables normally carry direct nice physical meaning, right. For example, if you see this this form, let us say this is spring mass damper for system, then what you have z is nothing but position, this is velocity. So, that definition is intact in your state variable. Now, if you see this definition what you see here, x 1 comes through this one actually, this entire polynomial what you have, x 2 comes through that actually. So, the definition of state variables are no more the direct physical meaning of the system dynamic equations. Okay. All right. Now, let us see a small example here. Well, let us say y of by ys by us is given in this form. Remember, this is already factorized and it is already a strictly proper polynomial. Okay. So, that b 0 term will not be there. Now, if I do this partial fraction decomposition for this, okay, which is actually very easy rather, let us try to do it here. Okay, 1 by s plus 1 and into s plus 2. So, what you have here is something like this. Let me erase this again and then try to do something. Okay. All right. So, what I have here is something like 1 by s plus 1 into s plus 2. So, what do I carry about with this 1 by s plus 1 into s plus 2. Remember, this will take something like a by s plus 1 plus b by okay, s b by well b by s plus 2. Okay. Now, what is a? A by definition is I will multiply this side. Okay. If I multiply that, I will get s plus 1 divided by s plus 1 into s plus 2. Okay. Okay. If I get that, if I evaluate, I have to evaluate that at s equal to minus 1, the roots of this actually. Okay. And it will turn out to be very nice actually, because if I simply multiply s plus 1 both sides here, what I get here, if I see that s plus 1, if I multiply s plus 1 and s plus 1. Okay. What happens here? This fellow gets cancelled out, and if I see s equal to minus 1, then this term happens to be 0. I am left out with only a basically. Okay. So, that is why this is given like that. So, what is happening here, s equal to like so what I am left out, this is gone, this is 1 actually. So, 1 by s equal to minus 1, right. So, something like minus 1 plus 2. So, this is 1 actually. Similarly, if I do b is nothing but s plus, now I have to multiply the other one, that s plus 2 I have to multiply. So, s plus 2 divided by s plus 1 into s plus 2 evaluated at s equal to minus 2. So, this is gone, I am left out to still 1. So, 1 by minus 2 plus 1. So, this is minus 1 actually. So, A is 1 and B is minus 1, and that is why you are left out with A equal to 1 and B equal to minus 1 here. Okay. All right. So, that is where you start with actually. Okay. That is so what I will do, I will take u of s inside, then x1 I am defining as that particular term. Okay. This is my x1 of s, this is my x2 of s. Okay. That is my definition actually. Okay. So, then I will carry forward and then tell, okay, this leads to what does it lead to? I multiply both sides, okay, s into x1 of s plus x1 of s, like that actually. So, I multiply that both sides. Okay. U of s is nothing but x1 of s into s plus 1, u of s is nothing but x2 of s into s plus 2 actually. That is simply coming from these expressions actually. Okay. And then I will tell, okay, I will formulate the differential equations here, that x1 dot, okay, x1 dot plus x1 is u of s. Remember that this expression what you see here, x1 dot plus x1 is u, and similarly x2 dot plus x2 is u. Okay. So, let me probably write it here also. Okay. What I have here is something like this. Say u is nothing but x1 dot plus x1 here, and u, these are all time domain actually. Okay. U is x2 dot plus 2x2. Okay. So, if I rearrange these terms, what I get here. Okay. If I rearrange this term, x1 dot is nothing but u minus x1, that is why here, and x2 dot is nothing but u minus 2x2. Okay. That is what I have here. So, now I will go back and put it in standard form. Okay, x1 dot and x2 dot, I will write it. See, normally the way to write it is you just leave this matrix blank and simply put x1 dot x2 dot here, x1 x2 here, give a blank matrix and put u here, and then try to see what is my x1 dot is minus x1 plus u. So, minus 1 here, minus 1 will into x1. So, that is minus 1 plus u, that means 1 here. Okay. That is how I will fill up the elements actually for every matrix. And then x2 dot is minus 2 x2. So, that is 0 into x1 minus 2 into x2. So, that is minus 2 here, and then plus u, actually u is 1 here. Okay. So, I get my A matrix here and I get my B matrix here that way. Okay. And then output equation, remember that what is my output here? Output is this expression minus that expression, right, multiply by u by the way. So, what it is? U by s plus 1 minus u by s plus 2, that means there is nothing but x1 of s minus x2 of s. Okay. So, that is that means y is nothing but x1 minus x2. So, if I really want to put it in matrix vector format, so again I leave this blank for a second and put x1 x2 here, and then see it is x1. So, that means plus 1 will come here, and minus x2, that means minus 1 will come here. So, this is my A matrix, this is B, this is C, that is all I have, and D is 0 obviously, and D happened to be 0 because I started with a strictly proper polynomial function, strictly proper polynomial, otherwise D would have appeared actually. Okay. Now, these are all nice thing about non-repeated root, what we saw here. Now, what about repeated roots? Okay. We will again see that in a example. Okay. Repeated roots, that means we have some expression somewhere like this. It can be partly non-repeated, partly repeated. So, that means we will concentrate here only that repeated portion, what is going on here actually. Okay. Now, non-repeated portion will go regular way, whatever we have discussed all these examples and all actually. Okay. Now, for repeated part, okay, let us say this some one term is something like this, then what we do? Okay. In that case, let me define my state variables this way. Okay, I will start with, let us say 3 times it is repeated, right. So, I will start with x3 as my regular definition, x2 is not u anymore here, but x3. Okay. x2 is x3 divided by s plus 3, and x1 is x2 divided by s plus 3. Again, there is a third order polynomial here. So, I will start with x3 definition, x3 is u by s plus 3 regular way, and then x2 is x3 by s plus 3, and x1 is x2 by s plus 3. And once this is defined this way, the rest of the algebra is fairly simple. So, you again do that multiplication and then take it to time domain. So, s into x3 is like x3 dot. minus 3 into x 3s is like minus 3 x 3. So, that is the differential equation, and similarly what you have here is x 2 dot minus 3 x 2 is equal to x 3, and remember it is not no more u, but x 3 here, and s into x 1, that means x 1 dot minus 3 x 1 is actually x 2 here. Okay. So, what I have here is something like x 2, okay, I mean this sorry x 1 dot minus 3 x 1 is equal to x 2. Okay. So, what I have here, this system of equations, if I really want to put it in state space form now, what I see here is x 3 dot is 3 x 3 plus u. So, x 3 dot what I have here is 3 x 3 plus u. So, that's clear actually. Okay. Probably this is a small mistake also here, this is 1 should have come here actually, it is not 1 0 0, but 0 0 1 probably actually. Okay. So, x 3 dot, okay, is 3 x 3 plus u. So, 3 x 3 plus 1 times u, okay. This is 0 actually. Now, if you see this one x 2 dot, okay. So, what is the 3 x 2 plus x 3. So, this is 3 x 2, okay, plus x 3, that means there is a 1 term here. Okay. Similarly, x 1 dot, I mean x 1 dot is 3 x 1 plus x 2, that means 3 x 1 plus x 2. So, what is happening? This 1 and 1 are appearing here actually. So, that is like a Jordan block actually. It is not a diagonal block, but it will happen to be this part of this overall system matrix will turn out to be a Jordan block. Remember, we are considering only one part here. Okay, other parts are non repeated, that is what you have assumed actually. Okay. Then that part will turn out to be diagonal, only this part will turn out to be a Jordan block. But if your original system is this, there is no other thing, then this is your system dynamics anyway. Okay. This is your this is how you will get into a matrix, this is how you will get a B matrix, then C and D matrix actually. Okay. So, this is how what will do for repeated roots. So, it is possible to get a Jordan form whether you have a non repeated root, okay. This is how we started with non repeated roots and all that, okay, and go ahead and do that. And if it is also possible to get a Jordan form even if there is a repeated root. Okay. And once again these Jordan canonical forms have some nice characteristics already. Now, what you see here are nothing but diagonal elements actually, I mean diagonal sorry eigenvalues, because even if it is a Jordan block, it is still a triangular matrix. Okay. And a triangular matrix eigenvalues are nothing but diagonal elements. So, you already have a diagonal I mean the eigenvalue information actually this form. Okay. So, they are nice properties of a Jordan canonical form. That is all I will probably discuss in this lecture, and we will see one or two more forms in the next lecture and then proceed from there actually. So, in general what we saw here is if it is possible to transfer from a transfer function representation to state space representation and vice versa as well. But what you should remember is transfer function given a state space representation, the equivalent transfer function representation essentially what you come up with system like a transfer function matrix basically, and that way is unique, that is given by a single formula C into Si minus A inverse in times B plus D, what that is the T of S. Whereas, the reverse procedure, that means given a transfer function to realize the state space representation, that is A B C D matrix, that is non unique, and depending on the particular application that you are talking about, the particular form can be of use actually. Some little advantage may come, but largely the properties of the system representation remains fairly same actually. That means, the eigenvalues do not change, things like that actually. So, more on that we will probably try to build on from there from the next class. Thank you.